Yeah, this is the lab. We're going to go over that in a bit, but let's some of these different pieces. Okay. I'm going to copy this data over into my temp directory. I should put it in SA. This interp data. And then I'll also, actually I should have copied both of those data sets over. So this one that says no data is actually, it has data in it. But it was more for examples. Okay. All right, so let's go back to the lecture, but I'm gonna be switching back and forth here. So now we're gonna start talking a bit about kriging, and it's like I said, it's not a mistake that we covered IDW last, because basically kriging kind of combines. When I say kind of, it's not exactly this, but it combines the element of a trend surface with an element of variability. In other words, how much error is associated with a certain area. In other words, if there's a trend that's easily identifiable, we could say that there is an amount of spatial autocorrelation that's occurring. In other words, if it's easy to predict a value at a certain location based on a nearby location because there's a trend going on, then the degree of spatial autocorrelation is high. Or if there's clustering, that also makes it easier to predict a value close by. So, and then there's some random variability in all data sets. So, one way to think about this is if we were at the water and we traveled away from the water, from the sea, towards a mountaintop, we would be generally trending up. We'd be going uphill. But we would sometimes go down, and sometimes go up, and sometimes go down, and sometimes go up, right? There's a trend associated with that. So what kriging does is it allows the user that's utilizing this interpolation formula to consider the fact that the ground or the surface is slowly trending up. And so when it predicts, it can use that information to come up with the next value. So if I'm using IDW to predict a certain area, I can weight those values that are further up the trend differently than those that are down the trend. I can change the way the interpolator works as I go up the hill. Okay. So I can take into account both the trend and any other types of predictions that I'm making. The stock market is not a non-spatial example, but what we're talking about there is that the stock market may be trending in a certain direction, but there's lots of volatility even in an individual day. So kriging similar to IDW, and then it weights the surrounding measured values to determine a prediction for an unmeasured location. That's the same. So the general formula for both interpreters is formed as a weighted sum of the data. In other words, we're still just looking at the weighted values around a particular value in order to, or the weighted values of all of the values in a particular search radius, or a fixed number of points. All right, so the weight in IDW, it depends solely on the distance. There's no other factor. Okay? We can square the distance, or we can cube the distance, or we can raise it to the power of whatever, but all of the weights for every single prediction are the same. They're uniform throughout the entire throughout the entire study area. They're always the same, and they're always just based on distance, a function of distance. Sometimes it can be a nonlinear function of distance, but it's always a function of distance. So for the same distance away any point is, it will be weighted the same. With the Kriging method, the weights are based not only on the distance between the measured points and the prediction location, but also the overall spatial arrangement of the measured points. So if the trend says that there's lots of change occurring, then it can use less points. Or if the trend says that nearby points aren't really related at all, there's lots of volatility in the data, then I can de-emphasize points that are even a little bit further away, and only focus on points that are very, very close. That's the way Kriging works, is that you don't really specify how you're going to weight the variables. You specify which Kriging method you're going to use, and it uses statistics to find out how the weights are going to be determined.
How would you know what statistical weighting you use based on?
We're going to talk about the different types of Kriging, and so you're going to make a decision based on that. Okay? So the process here is that first, well, you're going to make a prediction with the Kriging interpolator. These are the tasks that are necessary. First, you are going to look at your data to determine what dependency rules exist in your data. Does your data have a trend? Okay, if your data has a trend, then you're going to use a particular Kriging algorithm. If it doesn't have a trend, you're going to use a different Kriging algorithm. And then you're going to make the predictions. There are a little bit more Kriging processes that we're going to talk about. We're going to talk about the primary ones, the ones that most people use. So it's a two-step process. The first process is that the Kriging algorithm creates variograms to estimate the spatial dependence. We call that spatial autocorrelation. So it tries to find out if nearby values are related to each other. Okay, that's like clustering. And it tries to determine how far away do values get before I can't even, a nearby value is unrelated to a value that's way out there. So that's, if it decides, when it does the spatial autocorrelation, it could decide that a value that's very far away doesn't have any relationship to a nearby value, then I'm going to choose a smaller area that weights the nearby points more. If there's a trend to your data, it's going to predict, and it's going to use even far away points in making a prediction of a close point. So sometimes people say it uses the data twice to make the predictions. All right, so it looks at the variability in your data, the overall trend, and it comes up with a graph that basically looks at how your data is related to distance. It actually makes a different graph than this. It almost looks like the opposite. I'll show that here in a second, but it creates this graph. If we were to flip it over the other direction, we could call it a semi-variogram. And a semi-variogram is a graph that shows you about spatial autocorrelation. And it's telling you, as you get further away from a particular object, there's less and less correlation. But at what point is there no correlation? That's what the semi-variogram is telling you. It's telling you at what point there's no correlation between distance and the predictive ability to find out what that value is. So if you imagine, this is taken from the ArcGIS help, imagine a hillside, okay? This value here, the elevation at this location, this red point, is a number. And the nearby values are probably very similar to that number, right? As we get further away, the nearby values are way different than that number. And so what the semivariogram does is first, it creates a graph of all the point pairs. Each dot represents a pair of points. And these points, these 2 points for this dot right here, those 2 points are this distance apart. Let's say that represents 1. They're 1 unit apart. And this is how similar they are. In other words, these are only 1 unit apart, and they're very similar relative to the other things. Now look, this point pair way out here, right? It's almost as similar as this point right here that's only a little bit further away than that point. Let's say this point is 1.2 in terms of its distance. So that point right here, the second point along this line. And that value is almost the same as that value. Let me make this big for a second. Okay. This value right here is almost the same as that value, right, in terms of its similarity to each other. In other words, these 2 points are very similar, and so are these 2 points. Which point pairs, though, are further away from each other? Right. These 2 points are pretty similar, but they're really far away from each other. Okay. These 2 points are really far away from each other and really different. These 2 points are similar, but they're still really far away from each other. These 2 points right here are, remember, each point represents 2 points in geographic space. These 2 points are moderately close together and moderately related. So that's how you read that.
The pair of points that you're talking about, is that like the point you're trying to figure out and then another point off the side? So would it be the red point plus one of those blue points?
Exactly. So see all these lines? Mm-hmm. All of those lines are represented by 1 point. And actually, though, to answer, I think you were going a little bit further. So you can make a semivariogram just from a single point, but the semivariogram that it actually ends up making are every single point pair in the entire data set. So it's not just looking at 1 point.
Well, I'm saying is one of the points, that red point,
Yeah.
on every pair.
Right, but what I'm saying is,
That's what I was
is in this one that is the case, okay. But in the one that it actually uses to compute the data, no. So there'll be a point that also includes like the distance between those 2 points, okay. And how much they're related. Okay. Yeah. So anyway, this diagram right here doesn't look like it has a whole lot of value, but what this is telling you is that you see how this value kind of starts out like this and then it expands out. It gets bigger, like a funnel. That's the way almost all semivariograms look. They're closer together on this side, and they expand out like a funnel. So what this is telling you is that nearby points are pretty good predictors of other nearby points. But as you get to somewhere in here, it's hard to tell because we don't have a whole lot of points down here. But let's just say we had a ton of points. Somewhere around here, if we were to graph, this side represents semivariance, or degree of similarity. If we were to graph the degree of similarity, at some point it levels off. Put that right here. It levels off here, and the trend would just go right through the middle of this and stay pretty flat, right? And so anything beyond where that gets flat, so somewhere right around here, anywhere beyond where that is flat means that there's no more predictive power out there. In other words, we can't use points that are, if we put the line back down to here, we can't use points that are out here and this distance away from each other to predict the value of points that are that distance apart. Okay. And so what that means is if we were using IDW, if we're going to use this to go back to IDW, we wouldn't want to use anything beyond that range, because that would just mess up our data. Things that are this far apart aren't related to each other. So So that's one of the important mathematical bases. And the other important mathematical basis is that it just looks for the trend and uses the trend to predict values. And it says, okay, well, if there's a trend that's occurring, then I can predict the next value as a combination of IDW, plus I can add the trend and make it a little bit higher if it's on this side of the trend than on that side of the trend.
Are they trying to predict elevation? I'm not saying that the other data, but
Yeah, elevation is one thing, but you could also predict temperature using this. Yeah. Yep. Right. So what this formula says is basically that your value at the end is going to be a function of the trend and the semivariance, plus there's going to be some error associated that we just can't predict. I mean, there's some error associated with this. So we've got the prediction surface as the small dotted line, and we've got the trend as the solid line, and then the real surface might be the light colored line. Yeah, the third line, the lighter line. Yeah, it's hard to see. You can see it on the thing. Okay, so the trend surface in kriging, you either put it in or you don't put it in. So you either say, yes, I think my data has a trend, or it doesn't have a trend. So we're going to set that one aside for now and look at the semivariance concepts a little bit more. So semivariance is the value at which no more spatial dependence exists. In other words, there's no more autocorrelation. That's the SIL, not quite as useful as the first one I was talking about. So in other words, that's this value. Okay? The amount of similarity at which it levels off. But if the SIL is too low, in other words, the SIL is right down here, then there's really not any reason to do kriging. It's just saying that there's very little similarity in any of your data. You want the SIL to get up as high as it can. The range is really important. The range is the distance to the SIL, the distance at which no more spatial autocorrelation exists. That's what I talked about before. So the range is that place where it levels off. And then the nugget is the variation of the measurement errors combined with a spatial variation at a distance much shorter than the sampling space. Maybe I have a diagram on that. Yeah. Okay. So in other words, the nugget, what it is saying is that you don't have any points that are closer than the nugget, because it eventually drops off. So our nugget is this distance right here, because that's this height right here. That's the first point that we have. We don't have any points below that point, so we can't really adequately predict the spatial autocorrelation at points below that. Okay. So what that implies is whatever distance your nugget is at, you should at least be using that distance and probably a little bit more for your weights. So this is the point cloud of the points, and then this is actually the line fit through those points. So that's actually what the semivariogram is. It's the line that's fit through all those points. So this might be more idealized if the points really were this close together, which you probably would never see them actually that close together. But that's the nugget is this distance, the SIL is all the way up to there, and then the range is to the SIL, that distance, and that distance is related to the distance that you should include those points in your your process. So this is what it looks like. This is a tool called geostatistical analysis. You can run kriging as a standalone tool, but you can also kind of explore the semi-variogram before you actually run it. So in the lab, I don't have you do this. Maybe I'll do a demo of this, but you can actually look at the semi-variogram and look at the different models that it's going to that it could utilize. It's going to look at just the points in a particular circle. That's what this is. First one there, it's hard to read, but it says circle. So is it going to look at all of the points within a circle, or is it going to look at all the points within a sphere? And then there's also a bunch of other shapes that you could choose, but you can experiment with those. All right, so basically, if we have the sill and the range, those are the important ones, with the range being the most important. If your semi-variogram is noisy, that's what I said before. You know, if it's noisy, you're going to have a really tiny nugget. This one's actually pretty noisy. You have a really tiny nugget, and your sill is going to be really low. And what that means is that kriging is less effective usually, because there is not a lot of variability that can be predicted by how close things are. So you might see this a lot more in an elevation data set than you would in a temperature data set. In a temperature data set, things are going to be very spatially autocorrelated, right? Like the temperature here isn't significantly different than the temperature, you know, even 100, 200, 300 feet in a certain direction. But even in an elevation data set, in lots of elevation data sets, depending on the scale, kriging will still be appropriate. It just might not have, the semi-variogram might be a little more noisy than it would be in a different data set. So the longer the range is, the better kriging will do for you. Long range variation dominates. If you have a small range, kriging will still work, but it's only going to consider values within the range when it does its predictions. So maybe this should be actually indented here under here. What this implies is any pair of points beyond the range aren't correlated. There's no predictive power in any pair of points beyond the range. So here's some different idealized semi-variograms. And when you remember, they're derived from points, right? From point pairs, all the points. And so you actually have to fit a line through them. So you might fit a line through in a linear way, or in a spherical way, or an exponential way, or a Gaussian. In other words, it's like half of a normal distribution. And if you look at your data, you could see, oh, the points, they look like they're just going up in a straight line. And you can choose linear. If the points look like they're going up and they're leveling off, which is typically the case, then choose spherical or circular. If they're going up at a decreasing but steady rate, then choose exponential. So you can see the points and how they're calculated, and you're fitting a line to those points. And all this does, when you fit a different line to your points, is it'll adjust where the range is. It'll define what the range is, because the range exists where it levels off. So that'll have some effect on your overall outcome. Okay, remember I said that we're going to set aside the trend for a little while. So the trend basically is included or not included. If you choose ordinary kriging, you're assuming that there is no trend that you know of in advance in your data. Okay? So the only trend is the mean of the data itself, the average value through your data. So you're kind of assuming that without any additional information, that all the values should be constant. So ordinary kriging, this is just another slide. I'm going to skip through this because I'll actually demonstrate this here in a little while. So here is ordinary kriging surface. Here's another product, which is the standard error of ordinary kriging. Since this is a geostatistical method, it's predicting a value based on the trend and the autocorrelation. So it can tell you how far off its guess might be, or its prediction might be. And so what this is saying is that in the white areas, there's more confidence in the prediction than in the black areas. Those can be off. This is a map of standard error. In other words, it's the anticipated variability divided by the mean. Okay? So it's in unitless numbers. It's in the same units as the data. So if this is in parts per million, it's in parts per million. So we could be off by a lot of parts per million over here, 391 through 415, or in here we'd be off by less parts per million. So it's in the same units as whatever the units of your data are in. So if this was elevation in meters, the units would be elevation in meters. So it's one looking at that value. You can actually divide that number by the mean and get a unitless number, which would just tell you how many standard deviations it is out. All right, simple kriging. It requires that you put in a mean value. In other words, it doesn't calculate the mean value for you. You say the mean value should be this value. It's less. You would use this less commonly, but an application for simple kriging might be if you wanted to make a surface and you knew that the average value of your surface should be like 0. Let's say it's like I can't think of an example off the top of my head, but you have to pick out the constant mean value. You have to specify what it is. In other words, you know it in advance. So typically, you're going to use ordinary kriging over simple kriging because you don't know what the mean of your data should be. If it's temperature, who knows? Well, let's say you're trying to compare it though to the average annual mean value. Then you might use simple kriging. Okay? But typically, you're going to use ordinary kriging because you're just trying to predict the temperature value on a given day. You don't know what the mean for all of your area should be. So simple kriging is very similar to ordinary kriging in that it doesn't have a trend, but you need to specify what the mean value is. Typically, you're going to run ordinary kriging, or you're going to run, this is just showing the results, or you're going to run universal kriging. Universal and ordinary kriging are the most common ones. Universal kriging, you specify, yes, there is a trend in my data. And you have to specify whether it's a first order, second order, third order trend in your data. So if you run universal kriging, what you're saying is there's a trend in my data, and I want to use that trend to predict values. So I'm going to adjust values over here by the trend. Values over here by the trend. The predicted, the value, I'm going to use the neighboring values, whatever I find out is appropriate to use neighboring values. And then I'm going to predict a value, and then I'm going to adjust it by the fact that it's also going down in that direction. So that's what a universal kriging does. You can specify the trend, whether it's a first order trend. Here's an example of universal kriging. Because it has those two factors involved, it has both a trend and it predicts a value and then it adjusts it by the trend, you'll get things like this in universal kriging. You see how there's like adjustments being made? So particularly in areas that are almost on the periphery of your dots, because the trend can get really crazy. A trend surface can get really crazy there, right? What do we know about this area? we know that the really high values are right here and then all the way along the edge, right? And so in this area, if we just do a first order trend surface, it may not be appropriate, but we did just use a first order trend surface, or I did. I created it. We have a first order trend surface, and so the predicted value tells it, you just using the nearest values, it tells it to be high here, but then in some cases the trend surface also tells it to be really low right there, and so you get some messed up data in that area. It probably would be better, and I think more appropriate, because there is this undulation in the data, to use a second order trend surface there. Here's the standard error. Notice how high the error gets down here in this area. Now we're talking up into the 1000s. Okay. Here's another special case. This is called indicator kriging. Indicator kriging is actually really similar to ordinary kriging in that we're not looking at a trend, but instead of predicting a value, it just creates binary thresholds, 0 or 1 values. So instead of outputting a prediction, it outputs, is it over or under a threshold value? So you could actually do this as a two-step process, but the predictions are, it's just to predict whether something is over or under a certain value. The reason that you might use indicator kriging is, let's say every day you want to release an air quality map, and you want your air quality map to be these are the areas that are under high alert, don't go here, or wear a mask or something. And that's why you use indicator kriging, because indicator kriging says it's either above or below a threshold. So you're just going to get a 1 or a 0 value. So the output always looks like this, where you've got a 1 or a 0. Is it above or below the value that's been specified? There's the standard error. So what this is telling you, the standard error for indicator kriging should look really similar to the one for ordinary kriging. Probability kriging is similar, except for the output is the probability that it is above or below a certain threshold. And that's really similar to ordinary kriging as well. So it's probability kriging. So it's always going to be a value from 0 to 1. So you might say these are areas you definitely shouldn't go. You can turn this map into a hazard map because it's based on probability. And there's your. I'm gonna skip disjunctive kriging, but I'm going to talk a little bit about co-kriging. Co-kriging actually is a technique that uses more than one variable of interest at a time. So remember what kriging does is it combines spatial autocorrelation with a trend surface to predict a value based on neighboring values. What if you notice that there's another variable that is related that will help you predict variable x? So let's say that you're trying to do the salinity problem. You're trying to predict salinity. You could let's say that you also have all the river outlets, right, for the bay. You have all the river outlets. And so you input all the river outlets into the bay as points, and then you run Euclidean distance to the river outlets as and create a new data set. So what do you have there? For every single raster cell in the bay, you have the distance to the closest river outlet, right? Do you think that that's another thing that might explain salinity? Yeah, right? So you could put distance to a river outlet in as another variable that would help you predict salinity. So now you're trying to predict salinity in the bay, and you're using your input points. You're also going to use kriging as your method, so you're using the distance to nearby values. But then further, as another predictive variable in the model, you're going to use distance to the river outlets. So in addition to the autocorrelation, you also have cross-correlation between the two variables. So the example that this one gives here is ozone concentration and particulate matter might be related. So you could put one in to predict the other. So basically, it boils down to typically you're going to choose either universal or ordinary kriging. And what that means is you've got a trend. You've got a trend, or you do not have a trend. Ordinary kriging means you don't think there's a trend in your data. Universal means that there is a trend, and you want to use that in the predictive power. Okay? That's one of your choices. The second choice, which is a little bit, this is probably more important than this. That's your autocorrelation model. Whether you're going to include, like, what type of semi-variogram model you use. The default is spherical, which I think is appropriate in almost every case. But there are other options. Typically, you're looking in every direction equally to create that semi-variogram, but you can't actually tell it to only look in a certain direction for autocorrelation. So the default is which one's which? I always forget isotropic versus anisotropic, but you're specifying whether or not you're going to use points in every direction. How many points to consider, and it will predict this for you if you want. And then lag size, that is the average distance between points, and it'll also predict this for you if you want. But you can adjust that. You can make the lag size a different value. But typically, you want to use the average distance between points. Okay. I think rather than going through this workflow, I'll just show it in ArcGIS. Okay. I'm going to leave this slide up, and we'll go through this. In the lab, we're basically going to create a very similar diagram to this data. Okay. Okay. So I'm going to open up ArcGIS Pro, and I'm going to add the data that's listed in No Data to my map. Oops, I already got a map. So I'm going to go add data. I put it in CSA. It's right there. Oops. I somehow messed up. C10. Nope. All right. So in this one, I have a data set called US PPT stations.shape. So if I open that up, I have, I'm a little worried that it's not showing me the, is it just slow? Oh, maybe I'm out of the internet.
Yeah, some little message popped up and said check the internet connection so you don't lose your data from our
I wonder why I'm not connected to the internet. I mean, it's just a wireless connection, right? I mean, do you all use this same EDU roam?
That's what I put to on my phone. I will say this, our Wi-Fi gives me tricks because my phone always gets kicked off of it and I have to re-sign in. They don't do the sign up automatically well. I'm connected to it on my phone, so it should be running.
Now it doesn't even see it. I hope, let's see how far I can get. Like, I don't think it'll be a problem not to be connected, but sometimes it asks. So the the only problem here is that the background may have an issue every once in a while. Okay. All right, one important thing that I want to note here is that almost always when you're using anything that calculates distance, you need to make sure that your data is in a projection rather than being latitude and longitude. So look at this. This is in GCS. That's a Geographic Coordinate System, WGS 1982. So this data, although that's probably the way that the original data was stored in, latitude, longitude, and then precipitation values. If I open this up, that's what's in here. So, that's really dark. Maybe I should change this back to... I thought it looked pretty cool. General application theme, dark. Oh. I don't know if I want to restart it. I don't know. I better not restart it because I might not be able to connect anymore. So I think you could see it okay. I probably should have left it in the white mode for presenting. But you see we've got a latitude and a longitude value, precipitation per year, and temperature, the average temperature for the year. Those are the two columns that I have in my data, right? I want to make a surface out of this data. Well, this is what I'm saying. I need to first change this data to be in a projection that's appropriate. In other words, because I'm going to be using distance in my calculations, I can't leave it in latitude, longitude. Because if I do, the distance between these two points and let's say these 2 points looks very similar, but the distance between these 2 points is actually much less than the difference between those 2 points because the Earth is going closer together up there. Because of the curvature of the Earth, these 2 points and these 2 points are much different, although they appear almost the same, but this one's further north. The United States is not this much stretched out. So what I can do, the first thing I should do is to reproject my data. So I'm going to type in under analysis, tools, I'm going to type in project. And I'm going to project this data into a projected coordinate system that has real units associated with it. So I need to choose a appropriate projection. So since I'm talking about distance, I probably want to choose a equidistant projection. And I want to choose one that's tuned for just the United States. So I'm going to go continental and say North America and look for one that says something about equidistant North America. Yeah, North America equidistant. I'd rather choose one that says contiguous. But I might choose that one. Yep, USA contiguous equidistant conic. That sounds like a good one to choose. It's got the word contiguous US in it, which is my area, and then it's got the word equidistant in it, which I know is important because I'm going to be calculating distances in my formulas. So this one will allow me to do that. I would choose an equal area one if I was going to be really concerned about comparing area sizes. This one's going to make sure that the distances are correct. I'm going to say okay, or as correct as they can be. I am going to have to choose a geographic transformation, but that's just because of the difference in the datum. The datum that this projection is using is 1972. The datum that I want to use is 1984. So I'll choose that. That's fine. I'll just accept the default. This one will be called US PPT Station project. That's fine. I'm going to run it. I'm actually going to go to the map and go to the properties, and under coordinate systems, I can choose to have it match that coordinate system. The USA, contiguous, equidistant, conic. I'll say OK. And then that looks better, right? It looks more like I'm looking at the side of the globe. So now these 2 points that I was talking about before are in fact closer than these 2 points right here. They didn't look right before. All right, so now I can go about and make a surface from the points. So most of the surface prediction stuff is still in Spatial Analyst tools. If we open up Spatial Analyst tools, there is a whole tool set called Interpolation. You have IDW, Kriging, we talked about that. We call it Thiessen, but there's still this natural neighbor. Spline with barriers. We don't really talk about barriers, but we could basically say that a particular trend could not pass through a barrier. If we had like a water feature that we didn't want any of the splines to be able to pass through, in other words, we're saying, oh, there's no way that values on one side of the lake affect values on the opposite side of the lake, even if we're choosing the nearest 3 numbers. We don't really talk about these. Those are more just data conversion type things. Trend surface, that's one. In fact, let's start with that one. We're going to create a trend surface of the precipitation values. So let's take the US PPT station project, and we're going to predict, let's predict the average temperature per year using a trend surface. That'll be kind of interesting, right? So here is the output. What's the cell size? Let's choose a nice clean number instead of that number. These cell sizes are in probably in meters. They're in whatever coordinate system this is in. So it's in meters. So if we said 10,000, we're basically saying 10 kilometers. 10,000, right? So first of all, I'm going to do a first order polynomial. First order polynomial, and I'm going to leave it on linear regression. And I'm going to change this to trend US PPT _1. And that's going to stand for first order polynomial. So if I run this guy, I'm going to get a trend surface. And by default, it's just going to choose the minimum bounding rectangle of all the points as the study area. So it'll be something like this. So there'll probably be some points, maybe in the in extreme eastern Maine, that don't get predicted. If we wanted to change that, we could specify that in the environments. Specify that we wanted to use a different okay. So what is this diagram telling us here? Oops. What is this map telling us? So look at those numbers. These numbers are temperature, average annual temperature, probably in Celsius. Even in Celsius, this seem a little bit low. So I don't know exactly what they are. Okay. But what's the general trend there using a first order polynomial? Yeah, it gets hotter as you go south, right? Why is it tilted a little bit? What does it say? Like, how is the East Coast different than the West Coast? Just looking at this trend. Yeah, they get a little bit warmer further up north, which we know we know is true on the average for the annual, right? It gets more bitterly cold up here than it does up here. All right, let's look at a second order trend. I'm just going to change this number to 2, and all I'm going to do is change this polynomial order to 2 and run it. Okay. So now we're really starting to see the effect of continent on the average temperature trends for the year. So as you get into the middle of the continent, the trend is that it gets colder sooner as you travel north than at either end. So the water, we all know this, but we can see it in the trend surface. The water has a tendency to modulate or regulate the climate, so it doesn't get as extreme as it does in the center where it's all land. The water temperature stays more constant throughout the year. Right. The most I'm going to do 3 real quick. From this guy. So it's the third order. Now we can really see how the West Coast has a different pattern than the East Coast. What's that? So I think I have them both still turned on. So the first one is just fitting a flat plane through the surface. So that's why the plane is basically starting here and it's running in this direction. It's getting higher as you go this way, this direction. So there's only one change in one direction. Whereas here, there's one undulation in the data, so it's changing at a different rate, and it's not a flat plane; it's a curved surface. And then here, at third order, it's changing in 2 directions. Okay, so it undulates, and it has. You can see how it has one curve here and then another curve back over there. So you'd be able to see 3 curves in the data if you switched to a 4th order polynomial.
When you run it, it should put it right on the map, right? Like
Yeah.
when you run it.
Didn't put it in the map. Okay. All right. Now let's just do a IDW of the same data. So we've got our projected data, and we're going to choose temperature per year. And I'm going to change this back to 10,000 so that it's, I'll put 1 too many zeros. Okay, we're going to call this IDW1. Here is the power. Set the power there. The default is 2. Now we can either choose whether we want the search radius to be variable. If we set it to be variable, it's going to choose this number of nearest points. If we set it to be fixed, it's going to choose this distance, and it's going to take all the points within that distance. I'm going to start off with the variable 12. So it's going to choose the nearest 12 points, and still going to do those 12 points weighted. So the closest points will be weighted higher than those points further away. And the polyline features, if we wanted to put barriers in, but we're not going to put any barriers in. Like I said, if there was some reason that interpolation shouldn't occur over a particular area, then you put a barrier in. And that what happens is if there's a barrier anywhere within that search radius, it won't consider anything on the other side of the barrier from the search radius. Yeah. Yep. You can put a barrier anywhere you want. It has to be a line feature. And basically, if you can imagine, at every cell, it's considering either the nearest X number of points or everything within a circle. And if there's anything in that circle that's on the other side of the barrier, or if there's any nearest point that's on the other side of that barrier, it won't consider it. It'll throw it out. I'm running this. It's going to look a lot different. Okay, that's the IDW. So instead of looking at the overall trend, now we're looking at specific values. So things like little islands like this that are significantly colder than their neighbors, we'd have to go in and try to find out why those were different if we wanted to know. Okay, but now we see a lot of the individual variability in the data set. My guess is that particular point and this particular point and that point are all up high. The points that were associated with those values are up in the mountains. I don't know that for sure, but we can look real quick. I'm going to turn off. Somebody was complaining to me yesterday. They're like, I switched over to using ArcGIS Pro, and I can't. I used to be able to say turn everything off by right-clicking on the map. And I said, oh, I didn't notice that. But yeah, I guess it used to be you could right-click, and inside here it said turn them all off or turn them all on. Okay. So anyway, those are the points. And this is the IDW. So that point right there is pretty cold. Oops. That value. So it is up in the mountains. Of course, some of these others are up in the mountains too. So I wonder why the anomaly, why that one is so. Well, that one's pretty cold too. This one's in eastern Nevada. This one's in southern Colorado. I went camping like right here in southern Colorado. Actually, pretty close to there. Mesa Verde National Park in May, and it got below freezing. It was somewhere around here. It was cold. Anyway, but yeah, those look to be mountainous areas. Hey, that one's warmer than the average surrounding area, and actually it looks like it is out on the prairie instead of up in the mountains. All right, so that's IDW. What would we expect to see if we increase the number of points to consider in terms of how smooth this data set is? More smooth, yep. So if we increase that number, it would also take a little longer to process than it would. What about if we decrease the power? Will it get more smooth or less smooth? Decrease the power. If we decrease the power, that's kind of like where I made the mistake during the presentation. So it's counterintuitive, but as we increase the power, we're going to converge on nearest neighbor. And so it's going to only choose the closest point and weight that point the most. So I think I think it's going to actually make it smoother to go if we make this smaller. So this should be considerably more smooth than our other data set. Yeah, and it's IDW, so it's still not perfect, but we don't see as many of those holes that are out there. Let's change this. Even if this was go back to 12, I still think having this be 0.5 is going to be smoother. It's not. Oh, I overwrote it, so I can't compare it. But there's not as many of those things that are just out in the middle, islands of either hot or cold areas. All right, so those are all the deterministic. In other words, they produce the same thing every time you run them, and there's no prediction as to how accurate it is. Okay. Well, I didn't do all of them, but I did IDW, I did trend, natural neighbor, we went over sufficiently. Spline, you can run on your own, but we've got Kriging here. So Kriging has a lot more options to select. And so if we choose the same data set and we choose to do the temperature again, Okay. Here's the surface raster. That's the normal default value. Okay. Here's ordinary. Does ordinary consider a trend or not? Remember, ordinary versus universal. One of them considers a trend, one of them doesn't.
Ordinary doesn't have a trend.
Right. Ordinary doesn't have a trend. I think we should choose universal because there's a trend in the data. And we can, here you could specify whether or not it's basically a first order or a second order, a quadratic drift. And I'm going to, for this particular thing, we already looked at the trend, and it did seem to be that the second order trend would help because there's another thing explaining the differences besides just a single trend. Right? It doesn't, as you go north, it gets cold. It doesn't explain everything. There's some other trends that are associated with it. So I'm going to choose a quadratic drift. We could. There's no implementation here in geoprocessing for co-kriging, but we could include like elevation as another thing if we chose co-kriging, but we don't have that. So, all right, so I'm going to choose quadratic drift. Notice it does allow you to, it does specify, I'm going to go 10, 0, 0, 0. It does specify your lag size for you if you want. You can change that. Okay. Interestingly, the output cell size that it chooses is also related to the average distance between points. So it's predicting, it's using the same value for both of these, but not for the same reason. Typically, your lag size should be about the average distance between points, maybe a little bit lower. And same with cell size. You really want your cell size to maybe be just slightly below your minimum distance. All right, you can leave these blank if you want to. Usually people do because it calculate those as part of the process. You can force it to be a particular value, and what you're doing, particularly if you set the range, is you're forcing it to only consider points within that distance as it works. Let's just leave the rest of the things blank. But I also want to choose my variance of prediction raster. I want to specify that. So I'm going to just call this Kriging prediction and hit run. So there's my predictions. I might want to re-symbolize that. And then this map right here is showing me the trend surface. I'm sorry, not the trend surface. The prediction of my Kriging values. Now, just like that other map that I showed you before, particularly when we include a trend, I'm going to turn this data set on. Particularly when we include a trend, when we get into this area that's basically extrapolated, we get some really funky values that we should just throw away. Okay? If we ran ordinary Kriging, we wouldn't see this as much because we're not also including a trend. But the second order trend surface out here gets really strange, and then there's also nothing, there's no values to help us predict. And so when we're choosing the nearest 12 values here, it's like 1, 2, 3, 4, 5, 6, 7. It might be these 12. And if we move over, at some point, all of a sudden, it stops considering one of these values over here. And that's why we get these abrupt changes. So what I'm trying to say is, yes, it looks ugly over here, but that's okay because that data is no good. If we actually wanted to use this model in a data set, we would cut out this data. Okay? We wouldn't use that. It doesn't look right, but that's okay because that's not data we're considering. If we have, what we really should do is have a data set that shows us just the United States and cut that out, and it would look just fine in that area. Like the predictions wouldn't have the same weird values. Okay. we could like maybe clean this up a little bit by I should have included it. Well, maybe I did actually. I have that other data set that is the U.S. precipitation. Oh, there's the U.S. outline. I'm going to open up both of these. Yep. I'm going to remove that. Okay, so I've got my USA outline here. And I'm going to, I'm going to project it first. Project my outline to the same coordinate system as the PowerPoint station projected. Run that. And then I'm going to go feature to raster. Feature to raster. And I'm going to convert my projected data to the same coordinate system. Sorry, I've already projected it. I'm going to convert it into a raster, but I'm going to make sure that I choose the same coordinate system and the same snap raster as my other values. So I want IDW or Kriging. They all have the same size right now. Cell size is going to be the same as Kriging, and that should be it. So I want to make sure that it has the same grid as my other data. Run that guy. So now I have this data set that represents just the United States, and what are the values? These are some crazy values. But what if I want them to all be 1? Well, I can do that. There's probably a few ways to do that. Probably the easiest way to do it is to just say, if it's true, make it 1. If not, make it false. So now I'm just going to call this. USA raster. So what it's doing is it's taking the values here, and I don't know why some of them have a different value. I think it's probably because there are like little islands that are being included, and they all have different numbers. There we go. So now everything's a 1. All right, so what if I want, I'm going to delete this. What if I want to take this data set and use it to clip out this data set? Well, what tool could I run that will allow me to take the Kriging data set and turn all these values to no data? Actually, con will work. I mean, there's other ways that we could do it, but I could say if this data set exists, then give me the Kriging values, and if this data set doesn't exist, give me the non-existent values. So I think if we just run this, so this will be Kriging clipped. That'll be one way to do it. We could multiply them. We could do like a multiplication. So now we have our Kriging data set where it's just clipped to data that makes sense. What's this data set? Oops. Actually, yeah. Yep. So let's turn off the other Kriging one. Used to be an ArcMap. You could double click on these guys and choose the symbology. I wonder if you can still do that. You can basically steal the symbology from another map. I don't see it. So I'm going to click right here, and I'm going to choose classify, and then choose that color scheme that the other ones have. Well, maybe not. Be nice if I could find it. Which it's washed out, and it's. Is it just this one right here? It's kind of washed out, but it goes through all the colors like that. Is it that one? One more up. That one. I don't know. It'd be nice if it said, "Hey, show me one." But anyway, I'll actually go back and choose one of these. It just goes from high to low. So that's Kriging. Let's do a few more classes. 10 classes. So that's Kriging clipped to the right area. You can see that it doesn't have as many of those weird artifacts. Now there's still some issues here, but a lot of this has to do with the fact that there's mountains, and so we get some different predictions here than we do in other areas. Same with here. This is the middle of a desert. All right, so that's Kriging. We could also clip. It would be most appropriate, actually, to clip the prediction surface. And call this prediction clipped. So what this surface is telling us, again, I should probably change the symbology here. What this is telling us is that in areas that are green, there's less uncertainty about the value. In fact, those are in, what units are those in again? Whatever units the data's in, which I think is just degrees Celsius. So you can see in some of these areas that are really high, it's telling us that really the prediction's almost worthless, right? It's 25 that's 25 degrees. That's a big problem. These areas fall out of the range of values, or the range of points. So these areas up here, though, they're predicted a lot better. There's some issues with the middle of the desert and the mountains up here, but some area up here, those are probably also mountains. So these are the areas where it sees a lot more variability in the data than it's explaining with either the trend or the spatial autocorrelation. So what it's doing is this is a map showing you where the predictions still don't explain all of the variability in the map, in the actual data. So there's probably some other explanatory variable that we can include in the model that would help this, but there's actually probably multiple ones. Elevation looks like one of them. Precipitation is probably actually another one, right? So this is a big desert, and that's probably explaining that particular area right there. Right. The more green it is, the more confident it is in the prediction. Yep, exactly. All right. Now, ArcGIS Pro hadn't implemented this yet. Let me see if it's here. It hadn't implemented it earlier this semester, but they keep making changes. They actually just released this week a new version of ArcGIS Pro. So if you want to, well, actually, I don't know if everybody can do it on these computers, but if you have your own computer, you can go undo About, and if this says ArcGIS 2.3, it's been updated. that version was just released this week. Yeah. Oh, okay. I'll hit save. It's gonna crash right when I hit save. Yeah. Well, we haven't even really gotten into the lab. I'm just showing you stuff right now. So if it crashed, it's okay. But yeah, let's look here. What I was going to show you is that there is a geostatistical wizard. You guys have that or no? Do you have that on your versions? Okay. So geostatistical wizard wasn't, I forget exactly when they introduced it. It was like, it might have been 2.1 or something like that. But it's been around a long time in ArcGIS, in ArcMap, but they're slowly including everything because eventually ArcGIS Pro is going to take over ArcMap. But so they're including that. This works very similar to kriging in the tool, but it gives you a little more power. And the screenshots that are in the slides are actually the screenshots that are in the slides are actually using the geostatistical wizard, but it's the geostatistical wizard from ArcMap, not ArcGIS Pro, but it uses similar values. Now, in addition to kriging, there are a few other techniques that we didn't even talk about. We've got empirical Bayesian kriging and empirical Bayesian kriging with regression prediction, but we're not really going to talk about those today. But these are kriging with additional parameters associated with them and additional things to learn about. So if you want to dive in and learn more about those, you certainly can. This is something that they added pretty recently, this 3D kriging, which will actually predict a three-dimensional surface. So right now we've only predicted a 2D surface, and we're talking about how high or low that surface is. But what if we wanted to, what if we had points inside of water, let's say, or inside of the atmosphere? We had different values that we calculated at like 10 feet deep and 20 feet deep. We sampled at 30 feet deep, at 40 feet deep, at different locations. So this, they do this kind of stuff over at NASA with floats that they send out in the oceans, and the floats dive down and they collect salinity and temperature down at the bottom, and then they come back up and they report all their information. So we have not just two-dimensional values, but we have three-dimensional values. And if we want to predict a volume of information rather than just the values on the top surface, that's what this empirical Bayesian kriging 3D does. Is it basically creates a prediction at a bunch of different depths. So your output is however many rasters you want. Like let's say if you've sampled down to 30 feet, you have samples, some at the surface, some at 10 feet, some at 20 feet, some at 30 feet in different locations. It will use the same principles of kriging, but it will predict the values at 30 feet, 20 feet, 10 feet deep, all the way up. So you'll get a raster at different depths. Okay, so that's an interesting thing to look at, but we're not going to talk about it today. That's a more in-depth topic. Also, you can do some of the same things we talked about before. You can do inverse distance weighting right here in the geostatistical wizard. And the nice thing about doing it in here, what you'll see in a second, is that it actually shows you some statistics about your data as you walk through the wizard. We're going to do the wizard as a kriging one, and I'm going to choose my PowerPoint Station Project. Make sure that for the data field you choose one of these, either precipitation or temperature. I'm going to choose, I'll choose temperature again just to keep it consistent. And then if we want to do co-kriging, you would choose your other data set. We're not going to do co-kriging, so we just have one input data set. I'm going to hit next. And then I'm going to leave these defaults the same. Oh, no, wait. For trend removal, I'm going to hit that it's a second order, maybe even a third order. I'm going to say third order, just because we saw what looked to be an important trend, even at that third order. So here's my third order trend. That actually looks really similar to what we saw earlier when we calculated the third order trend. Again, here I'm just going to choose the defaults. There's literally a ton of different things that you could learn about here, but the defaults that it chooses, like the ESRI likes to say, we choose good default. They try to choose good defaults here. All right. So this is showing you your data in terms of the density of your data. Looking at, let's see, this is just looking at the values. So most of the values are, this is a histogram of your data from the low values all the way up to the high values. All right, this is the semi-variogram. Well, actually, this is the covariance. So let's look at the semi-variogram because that's the way we explained it. I like to look at the covariance. So, I like to look at the semi-variogram. So it looks like you can see this trend going up. These are all the individual lag points. So it looks like the sill is kind of hard to define here, but but I would say it's occurring somewhere right around there. You can try to change a little bit. Just hit optimize model. There we go. So what it's done is it's picked the best parameters to make the range the easiest to predict. So it's used trying to see which model it used. So there's the range that it found. It didn't use anisotropy, so that is using all directions. Maybe that's not until the next one, but you'd think that it would have to choose which model that it was using. There used to be an option to do that. See from the slides here. This is what I'm talking about. There used to be a way to choose the model. But maybe when I hit optimize model, it just chose it for me. I'm going to hit next. And here I can choose whether or not I want my my neighborhood type to be smooth or standard. In other words, the points that I'm considering are around me. I'm just going to leave the defaults again. And then here's the cross-validation. So the cross-validation summary tells me that what the average error is. The root mean squared error is 1.35. So what that means is that on average, the distance between the modeled surface and the real surface, if I take all those distances and I square them and I add them all up and I divide by the total and then take the square root, I get this number right here. And it's in the same units that you're working in. So 1.35 degrees is the root mean squared error of the prediction. So we should expect some pretty good values. Did I just close it? Oh no, it's this one, right? Nope. I think I just closed it. Oh, so there it is right there, Krieging. I'm going to close these other ones. So this is the Krieging layer, and the geostatistical wizard actually produces a virtual data set. So this data set is virtual, and I have to right-click on this and say export layer in order to get it to be a raster, because right now it's just a graphic in your data set. So you could save it and open it back up, and you'll get to it again. But that's following the geostatistical wizard through. It gives you a lot more control, but there's a lot more options that you have to deal with and use to predict your values. You can't use the geostatistical wizard in Model Builder, but any of the tools that we ran, like you can run all the geoprocessing tools that we ran earlier, including Krieging. You can run right from the tool here. So under Spatial Analyst, under Interpolation, you could build a model that used IDW or that used Krieging. And I'm not actually sure if there's a raster function that does interpolation, but I kind of doubt it because they mostly operate only on raster data, not on vector data at all. So yeah, there's not one.
So once you export that data as a raster, you come back in and work on it.
Yes.
Like
Yep. You could export it from this as a raster and work on it either as a raster function chain or in the toolbox. Okay, so let's talk about the lab here real quick. Let's see how long this has been going for. It's been going a long time. Okay, so where is my lab? I have way too many computer tabs, you're right. You're not the first to make that observation. Okay, so here is the lab. I think it's already open. Yep, sorry, it's already open. Okay, so what you're going to do is on the course website, you're going to download the data, copy the entire folder, and inside there are several shapefiles and grid coverages. I'm going to talk about those here in a second. So there is a DBF file that came with this text. We actually used to use this text for this class, the whole text. But it's a really thin book, and it was like $150. So we don't use the whole book anymore, but I still use this chapter. So it contains the soil data that came with the data. So ArcGIS can import this soil data. So we're going to do that together in class. Okay? So then we're going to mask it, just like we masked this data. We're going to mask our data to a certain area, and that way we'll avoid the nonsense, the stuff that's extrapolated. And then we're basically going to do a number of interpolations. So I'm going to walk you through using zinc. So you, as part of this lab, are going to use one of the other non-zinc variables. You can use cadmium, mercury, lead, and what you're going to do is do this. Okay? Basically, what you're going to do is you're going to create a table that's similar to this table here. Except I'm not going to ask you to do as many methods here. Or as many, you're basically going to compare how different different interpolation algorithms can get. And so what I want you to do is, if you choose cadmium, I want you to take the cadmium data set and run it's going to be 5 different interpolation methods on it. Report the minimum value, report the maximum value. Then you're going to choose an arbitrary value that's in the middle of your data. In other words, don't choose some value that's outside the range of your data. So once you run the interpolation, so let's say your values range from 206 to 770, pick a value like 500 that falls in the middle of those values. It doesn't have to fall exactly in the middle. Pick a value, and then you're going to tell me the percent area that's greater than that. Okay, you don't have to do this twice. So you're going to have just these 3 columns. Percent area greater than some arbitrary value that you choose. So this is going to change with each of your data sets. And you're going to have to think about how you could calculate that. Okay? Can you get this number from just the number of cells? You can, right? So all this is basically a conditional operation or a true-false operation. You just say, is the predicted value above or below 500 or whatever number you choose? And then you open up the attribute table, and you'll get 2 values, and it'll tell you how many cells are in each. You actually don't even need to convert them to real units because the cells are surrogates for area, right? And you're only calculating the percent. So if one of the, if in your raster data set, it says you've got 100 cells that have a value of 1 and 150 that have a value of 2, what's the percentage of ones that have a value of 1? Well, you take 100 plus 150, and you divide 100 divided by 250, and that's the percentage. So we'll walk through that too. But that's what I'm explaining here. So yours is going to have, I said 4 columns. Minimum value, maximum value, percent, and then the mean absolute difference. So we'll walk through calculating each one of these for zinc. We'll do that together. All right. So the first thing I'm going to do, I'm just a little worried about this closing because it doesn't look like I'll be able to reconnect. So I'm going to insert a new map without getting rid of my old map. But I won't have a background. It doesn't really matter for this one because it's just such a small area. So I'm going to add in, I'll just get rid of this topographic one. And I'm going to add in the data that I got for the lab. Insert, map, add data. There's not too much data to add. Go up to Interp. That's the data you're going to use for this lab. And just add everything. You actually don't need the landmask.shape. So I used to make you make the landmask yourself, but I already made it. So I'm going to change this color scheme. Huh, looks like it's broken. Zoom to layer. Okay, no, it just wasn't zoomed to it. So I'm just going to choose, that's as good as any actually. I'll choose classify. There's really only 2 values, 0 and 1, but there are hardly any zeros. So the land mask is the area that is land. Okay. This data set is the flood mask, which they refer to in the textbook, but we're actually not going to use it for the lab. It's the flood frequency data. So we'll just turn this off for now. We'll leave our land mask on. And then we're going to look at this standalone table. If we open up this standalone table, this is where we have our zinc data. So you can't use zinc, but you can use any of these others, lead, mercury, cadmium, because we're going to do the zinc one. We're going to do that one ourselves. We're going to do that one together. Right? But one of the problems is that this data isn't spatial. This is just a data set that's a table. If we want to turn this into a spatial data set, what we have to do is right-click on this and go up and say Display XY Data. That will allow us to turn tabular data into a spatial data set. Huh. Maybe we have to specify. Let's specify the, so would the easting or the northing be the X field? Yep, easting, because you think about it, you go east-west, that's better, and the northing will be the Y. Oh, man. It's not working. I wonder if this...
I'm doing fine up here.
Yeah, I'm just wondering if this is related to my license not working. Is everybody else's working? You don't get a red X right here? No. Okay. Yeah, it must be related to my license not working. Let's see if I can overcome this issue. Well, somebody could just create a shapefile and send it to me. This looks like it's related to Python, actually, but that might be related to the fact that I'm not on the internet. Yeah, this is going to go to the internet. Okay. Well, I can just use ArcMap, just for this part, and then I'll import it back into Arc. No, it'll don't choose a coordinate system. This data is not really in a coordinate system that ArcGIS knows about. So leave the coordinate system blank, and it's not going to be in a coordinate system. But it'll be in the same coordinate system as the map, as the land mask. So this is going to pop up real quick, and I'll be able to. I'll be able to fix this. My what? No, but the tool that I need to run for some reason isn't running without the internet. The tool that I need to run to do the XY data, it says that there's a problem running it. So I said that this was in CSA, Interp, soil pollution, and then I need tool, then I just need to go right click, data, display XY data, so it's the same words, easting, northing. I'm just going to leave this blank, say okay, there's my data. Now I can say data, export data, and I can save this. I'm just going to put it back in C temp or C SA interp and call this. Oh, sorry, that's my name. I'll just call this soils data. And then hit save. Okay. I'm not going to add it there. So for you guys just put easting, northing, and that's all you need to do. Don't worry about the Z field. Don't put anything in coordinate system. Just hit run.
Ours is insisting on
4 in the coordinate system.
What happens if you run it? Does it show up on the map?
No.
Okay.
Not at all.
Yeah, so choose current map. So under a coordinate system, choose current map and run it. Does that work?
Yay.
Okay. All right, so I'm going to add my data set back in here. I'm going to go to map, add data, choose. Did I put it in the wrong place? Oh no, I just need to hit refresh. All right. So now I've got my data. I can close this. Okay. So that's my data. I don't know what these 2 extra points are. What's that? Yeah, everybody's got them. So I could symbolize my data like I did in the lab, where I show zinc as one of the values. Using graduated symbols. Yep. So if I choose zinc here. Go. So that's kind of, with obviously different colors, but it's the same basic symbol as we had way back up here. Remember when? Anyway, I don't know where it is. But. Okay, so what we're going to do is we're going to go through the workflow of what you need to do to create the table. So what I want you to do is what I want you to do is your chart is going to have 4 columns, and it's going to have how many 4 columns, how many rows? So I want to see at least 5 examples. So you're going to have 5 rows. One is going to be an IDW. One is going to be a spline, and you can choose each of these. You're going to do 2 different Kriegings. You know, you could do one ordinary and one universal Krieging, and then one other. You can choose. It can even be another IDW or another spline, but you could also do the trend surface, let's say. So you're going to run 5 interpolation algorithms. You're going to run one of these, 2 of these, and then one other of your choice. And all the parameters that you choose for each of these, they'll also be of your choice. You can choose to be whatever you want. So then, once you do that, these will be your rows. So if I'm gonna make my table, here's my next sheet. I'm gonna have my IDW. I'm gonna have my spline. I'm gonna do universal Krieging, ordinary Krieging, and I'll do a trend surface. Okay. So those are going to be the 5 that I do. What are the columns? What do the columns need to be? Well, the columns need to be minimum, maximum, percent area greater than X. You choose X, but make it interesting. By that I mean it should be in the middle of your range. And you choose the mean absolute distance from IDW. So I'm going to put min, max, percent area greater than, I don't know what my number is going to be yet, so I'm going to put a question mark. I'll come up with that number later. And then this one's going to be mean absolute difference from IDW. And what I mean by difference from IDW is this IDW. So keep that IDW data set around. So by definition, we already know this is going to be 0 because this is the difference from this data set. So all these other values will be the difference from that first data set. How much difference there is. So there's no difference between the IDW data set and the IDW data set. Now, if you choose to do a second IDW data set down here, which is perfectly valid and might even be interesting to compare you know, IDW with the 12 nearest neighbors to IDW with the 6 nearest neighbors, then you just have to remember that that second data set is still going to be compared to the first data set. They're all going to be compared to this first data set. All right, so let's see how do we fill these out, okay? These are actually just part of your statistics. Once you calculate the value, you'll get the minimum and maximum in the statistics. So if I go back over to here, my first task is to run and create a data set for this area. So what I'm going to do is go back to IDW, and I'm just going to choose all the defaults. You're welcome to tweak this a little bit if you want. I'm going to choose all the defaults. My soils data is going to be my input point features, and zinc is going to be what I'm going to choose as the layer. My output raster, I'm going to keep track of it, so I'm going to call this IDW1 as my output raster. Okay. It's very important, well not very important, but I want you to use the same cell size and extent as this data set that's already there, this land mass. So what you can do is under environments, just choose, for the coordinate system, choose landmass 2. For the snap raster, choose landmass 2. For the cell size, choose landmass 2. And for mask, you can even choose landmass 2. Yeah, should be good. Okay, and then run it. Once you run it, should look like that. Why didn't it? Under environments, let's go back and change extent. I forgot that one to landmass 2. Okay. All right, now run it. Again. Right? See how when you did that, it already cut it to the boundary that you needed. Why do you think it did that? Which one of these sounds like it flipped it to that area? I almost said it. Snap raster, that's a good guess. Snap raster just makes sure that the corner is the same corner. It's masked. So extent makes it the same size. And realize that there's still a bunch of no data values out here. Still a bunch of no data values out here. If I want to symbolize this differently, I could change it so that I could see those no data values. Yes. So I just chose, you're welcome to choose different parameters. Anyway, what I was going to do is I was going to change, if I change no data to red, there would be a bunch of red cells right here because this raster still exists out into this space. Okay? It's not like clipping it. It's masking out those values. So that should give you a better clue. So mask is what takes anything that's no data in your mask and it makes it no data in the output. So it kind of like has the same effect as doing the thing and then multiplying by the mask data set by ones, and ones here and zeros and no data here.
So we keep trying to colorize the no data so you can show the no data.
I was just trying to show it to you all. But yeah, I'm not going to do it. But the point is, that's what mask does. So extent, that's the one I forgot to do the first time. That makes sure that the extent is the same size. Snap raster makes sure that the corner is in the exact same place. Cell size makes sure the cells are the exact same size. And then mask makes sure that anything that's no data in the mask is also no data in the final output. So that's why that looks like that, where it's clipped to that area. And this is what we want. We can start making our data set work at this point. So it looks like that. That's great. And what we need to do here is if we right-click on this data set and look at its properties, it will show us under, yes it is under metadata. Yep, it's under source. Under source, if you look at the statistics, it will show us the minimum and the maximum value right there. Okay. So you can click into here and say Control C. There's the maximum value. Click in, Control C. I didn't get the last number, but it doesn't really matter that much. Okay. Control C. So now I've got the minimum and the maximum. Now, at this point, I can choose what my interesting value is going to be, right? So if I look, in fact, one value to choose that you know is going to be in the middle of your data is just your mean. So what don't I'm not going to choose the exact value, but I'll choose 400. So I'll choose 400, let's say, for this data set. Now, if you choose zinc, and if you choose cadmium or something like that, your value is obviously going to be different, but you're welcome to also choose the mean. So what's the percent area greater than 400? How could I find that out? Remember that what I'm really asking is how many cells are over 400 versus how many cells are there total. Right? That's what I'm really asking. So all I need to do is run, what type of operation could I do to ask that question that would help me to assign all the values that are greater than 400, or is it less than 400? Yeah. All the values that are greater than 400, one, and all the values that are less than 400, a different value. I could do it in raster calculator. I could do it in con. I could do it in reclassify. There's a few different tools that would work. Okay. I'm just going to use con. So I'm going to take the IDW, and then I'm going to add a clause and say if the value is greater than 400, I have to hit add. Oh, sorry, I guess I did do that too fast. So if I say IDW, if the value is greater than 400, then make that the clause. So if it's true, I want to make my values 1. If it's false, I want to make my values 0. So in other words, where's it going to equal 1? It's greater than 400. Yep, I think you were on the right track there. Okay, it's going to equal 0 where it's 400 or less. And I'm just going to call this, I'll call this IDW calc. It doesn't really matter what you call it, and run it. Once you run this, it creates a data set that is not continuous. So you just have zeros and ones. So it builds an attribute table. You can right-click on it and hit properties. And by doing so, sorry, not properties. Right-click on it and say attribute table. By doing so, you will get the count of all of those values that have a value of 0 and all the values that have a value of 1. That's what this number means. So, although I didn't ask for this information, you could put it off to the side here. Okay, so this is all the values of 1. This is all the values of 0. So what we really want to get that value is what? How do we get the percent above 400? Yeah, so we divide this number, the total. So it would be this plus this. And then if we really wanted to make this a true percentage, we could just hit that percent button. So 37% of the values are greater than 400. The mean absolute difference from IDW, like I already said, is 0. So we still want to discuss how to do this together. So I'm going to go ahead and do my first spline, and we'll get all of these values for the spline. I'm not going to go through every single one of these because they're going to be the same workflow. Okay. But let's go back and do spline under geoprocessing. This is all that I'm requesting while I'm with a short report. I could save it. Well, actually, I do also have you turn in a map. So make a small report. Things you should look for. Okay. Make screen capture. Highlight these in the graphic. Make screen captures, one per layer created to illustrate. You could. What I'm telling you to do is to do the snipping tool. Everybody know how to use the snipping tool or not? You hit the Windows button, type in snipping. You can just cut and paste this into Word. Okay. So let's do spline, and we still need to input the original point features, which is the soil data. Make sure that your Z observation values are the data that you're looking at. And then at this point, what you need to do is I'll just call this a spline 1. At this point, what you need to do is make sure that you go over to environments and choose all the appropriate values here. Coordinate system you can leave blank. But remember, extent is the one we need to change. So we want to make sure all these are landmass, same as landmass. Landmass 2, cell size, landmass 2, mask, landmass 2. And that should all be the same. Okay, you're free to change these if you want. You don't have to. These are the defaults for spline. I'm just going to choose to run the defaults and run. And I'll get an output, and it'll just be for this area. There we go. That looks right. Now if I open this up, if I go to Properties, and I go to Raster Information, I'm going to look at the minimum and maximum. That's under statistics. There's the minimum and the maximum. So copy those values over into Excel. So this one, I didn't get all the value. I didn't get the whole value. There we go. What's that? Oh, sorry. So I'm going to change this to landmass 2. I'm going to change snap raster to landmass 2. I'm going to change cell size to landmass 2 and mask. So those 4 things: mask, cell size, snap raster, and extent. You don't have to mess with coordinate system. I right-click on it and say Properties. Yes, and that's where I get the statistics. Make sure that you copy the whole thing, though. I didn't actually. I messed up. Okay.
Did you mean to do lead instead of zinc?
No, I did not. Thank you. I was wondering why the value.
In case anybody's numbers don't look right, I just figured that might be.
No, you're totally right. Yeah, I was wondering why my numbers were so wrong. I mean, I didn't think they were wrong. I was wondering why they were so off. Whoa. Well, they're still pretty off, but the mean is actually pretty close to 400 still. Okay. All right, they're still pretty different. Now, one way that we can explain why they're so different is that spline uses like little trend surfaces everywhere, and so it's more prone, especially on the very edges, to get way different. Okay. So that might be why it gets so negative right here, because of there's no points out here past the edge. So this is really not a good prediction, probably, because it's using a trend surface there, and the trend is going off into nowhere.
Those numbers are
Outside see how there's no points way out here, and so that's really extrapolation. And trend surfaces are much more susceptible to extrapolation issues than the other deterministic algorithms like IDW. See, IDW, because IDW is only using the closest X number of points, it's still just relying on these points. And it's still not a great guess, because there could be some higher values up here in reality. So extrapolation is never a good thing, but your extrapolation for trend surfaces is going to produce more weird values than your extrapolation for IDW.
So your the higher numbers are the outliers. So the outliers you don't do anything with them, you just explain why they like that.
Yeah, and notice that the very highest value actually is not that different as the very lowest value is going way negative. See how negative it's going down here? So that's the actual lowest values are the big ones. Okay, so how do I calculate the percent area greater than 400? What did we do? Did we end up doing con? So let's do it a different way this time. You want to do it in the raster calculator? All right, so we got our raster calculator. We're still going to do this as a con, so we could go con spline 1 is greater than 400, comma 1, comma 0. So now what we're doing is we're saying, if spline 1 is greater than 400, make it 1. If not, make it 0. So we're really doing it the same way. I think that's a fine name for it. Leave that up for a second. I hit run. Ooh. I'm having the same problem. It's probably no. You don't really need to change your environment since you're only operating on one raster. But that tool isn't working for me. Probably because it has to license it online somehow. But it should work for you if you want to do it. I'm going to go reclassify, which is a tool in Spatial Analyst. So I just take my data, and I'm just going to go to classify, and I'm going to say there's just 2 classes. And I'm going to say it's going to go to 400. This is going to go from 400. This will be 1. This will be 0. I know that's really hard to see up there, but what I did was I basically just set the upper limit of class 1 at 400 and the lower limit of class 2 at 400. And so it should just be an alternative way to run, to do the same thing that we did last time with the conditional tool. Well, I just asked you to choose a value that was inside the range. And so for the first time, when I ran IDW, I discovered that 400 was going to be in the range because it was very close. The mean was like 400.6 or 406 or something. So you're going to choose a different value, but you're going to use the same value for all 5 rows in the table. So now I can look at this and say, oops, that's the wrong thing. I'm going to look at this and say open attribute table. and that's going to be that value and this value, and then I can actually just fill this down. So now only 30% of the values on my spline are above 400. The point here is to show you how different interpolation algorithms can be. Okay. So this one has a lot less values, 7% less values over 400 than the previous one did. All right, so how do we calculate this mean absolute E? Didn't spell absolute right. How do we calculate that? Well, how do we calculate the difference between two data sets? Yeah, well, I'm just looking for the difference, so we just subtract. So minus, and I'm going to take, we're actually going to be looking at the absolute difference in the end, so it doesn't really matter what order you do these in. So I've got spline and IDW, and I'm going to get minus spline here to run it. But right now I've got some negative and some positive numbers, so I could run the ABS tool, which is the absolute value tool, and choose minus spline, run that. Now I have the absolute, this is the absolute difference. Okay. So I zoom out here and turn this off because it's getting distracting now. So what this is saying, the white values are the highest values. So what do the white values represent? What are the white values saying? It's not really confidence. It's just, I mean, we might turn it into confidence, but it's not directly confidence. It's the difference between the IDW interpolation and the spline interpolation. So it's showing you where the IDW is really different than the spline interpolation. Not surprisingly, down in this corner, right? But this area right here, which is still far away from other points, is also very different. IDW versus spline, it's a very different. It's very different in terms of how it predicted that area. The white means it's a big difference. So I subtracted my IDW interpolation, which was using the same data, the same zinc data, from my spline data set, and now I'm symbolizing the differences. So the higher differences mean that there was a bigger difference between those two. The goal of the interpolation algorithms is identical. It's to create a continuous surface from your data. But it did it in two different ways, and there were some significant differences in how it did it. So to get the mean now, I could just right-click on this guy, say Properties, Statistics. There's the mean. So this is the mean absolute difference between those two data sets. 160. So that's the average distance. So I'm trying to predict, zinc, the amount of zinc in the soil. And just using a different interpolation algorithm, on average, means that I get a difference in value of 160, whatever units they're in, parts per million, I think. Okay. So I could decide whether that's significant or not, but it's interesting that doing two different activities that are supposed to have the same goal can produce a significantly different result. So anyway, what you're going to do is continue to fill out this table for your variable of choice. So you should have 5 rows. Now, of course, trend is, if you do choose to use trend, it's going to have some very different values. It's going to have the most different values. But one one thing you have to do is take that with a grain of salt, because unlike the rest of these, trend is not necessarily trying to produce a surface that is a prediction of the actual values. It's more for examining the trend itself. So anyway, you're going to turn in this Excel sheet. You could cut and paste it into Word if you want. You're going to make a small report less than a paragraph, or about a paragraph. Yeah, so you're going to note where differences are large and small, so differences in the data. So look, this is something that you're going to say, well, one thing that we notice is most of these differences occur in areas where there's not a whole lot of points, right? So the differences here occur in areas where there's not a whole lot of points. That would be interesting. Maybe when we do the trend surface, the differences occur in different areas. Maybe when we do the kriging, the differences occur in different areas. I think a lot of cases it's going to be in areas where there's not a lot of points. So, yep. So then create it in your Word document. Put a few of the screenshots in there, and then turn it in. So I forgot to change this from last time. It should say I don't want your ARPX file. You don't want the project file. I want a Word file, or perhaps an Excel and a Word file. Okay. That's what you should turn in. Does anybody have any questions about that? About what you're supposed to turn in? You're just going to run this process 5 times and create this this sheet, create a few maps, and talk about the differences. Basically, as I already said, the purpose of this lab is to help you understand that the interpolation algorithms can create quite different outputs, and which one's right and which one's wrong is often not just like this one's always wrong and this one's always right. You have to look at your data and find out which one is the most correct in your particular scenario, for your particular data set, because it matters how close your points are, matters what type of data you're trying to put together. There's lots of research articles that just look at the best interpolation algorithm for different processes. So for different different processes is a fine way to say it. All right. I'm going to go ahead and hit pause. I'm going to